students, it's Miss Bettis and Grogu here, and I am going to teach the lesson on the second derivative test myself. Sometimes when you want something done right, you just kind of have to do it yourself. All right, so let's get into this lesson. It should be fun.
Let's start with a warm-up. Let f of x be as defined here. It says find the intervals on which f of x is increasing or decreasing and find local extreme values. So let's remind ourselves of a few things. F of x is increasing when our derivative is greater than 0. It's decreasing when our derivative is less than 0. And it says find the local extreme values of f of x. Now, we can find those values using our first derivative test. But let's go ahead and get started. So f prime of x is equal to 3x squared plus 6x. If we are looking for our critical values, we need to set this equal to 0. I'm going to go ahead and factor out the 3x. And we find that our critical values are x equals -2 and x equal 0. Okay? So you can make yourself one of these sign charts, and we'll go ahead and put our x values on the chart. And these locations are where our derivative is equal to 0. We are concerned with what is happening in each interval around these critical values. So from here, we can construct ourselves a table to figure out the behavior of our function. I like to construct a table in this manner, especially when you have factors or you have a function that has been factored. It's sometimes easy to see things when you write it in this format. All right, so I'm going to give myself some values in each of these intervals. So on the left of -2, I'm going to use -3. In between -2 and 0, I can use -1. And to the right of 0, I can use a +1. Okay, so if I put in a negative value for my first factor, this is going to be negative. For my second factor, a value of -3 is also going to make this negative. So ultimately, the sign of my derivative in this interval is going to be positive. So I'm going to put a plus right here. And this just gives me the sign of the derivative. All right, let's look at -1. If I put a -1 into the first factor, it's going to be negative. If I put a -1 into the second factor, it will be positive. And then ultimately, this gives me a negative derivative in that interval. And lastly, I have a positive, which again is positive. So what does this information tell me? It gives me the behavior of my function. And for these values, because my derivative is positive, then I know that the function is increasing. Where I have a negative derivative, my function is decreasing. And lastly, again, here it is increasing. So now we have found the intervals of increase and decrease. We'll formalize it at the end. We can locate our extreme values using our first derivative test. So at -2, because my derivative goes from positive to negative, I know that this value is going to be a local maximum. And at 0, because the derivative goes from negative to positive, I know that this value is going to be a local minimum. To find the value of our local max, we're going to substitute in a value of -2 into the original function. This is -8 plus 12 plus 2, and that gives us a value of 6. And then we'll substitute in 0 to find the value of the local minimum. That one's easy. You have 0 cubed plus this will also be 0, and our constant is the value. So let's summarize for this problem. Be sure to pause the video to make sure that you have absorbed all of this information. But it says here, our f prime is greater than 0 on these two intervals. Therefore, f of x is increasing on those intervals. Likewise, when we have a negative derivative, we have f of x is decreasing. Lastly, we want to say that f of x changes from positive to negative at x equals -2. Therefore, that creates for us a local maximum at x of -2. The local max value is 6. So because our derivative changes from negative to positive at x equals 0, that creates for us a local minimum at x equals 0 with a value of 2. Let's move it on. So how do we use a second derivative to inform us about our function? Well, the first thing that we could do is we can do the concavity test. And the concavity test simply says this: if your second derivative is positive for all x in a particular interval, then that graph is considered to be what we call concave up. If your second derivative is less than 0 or negative for all x in a particular interval, then that graph is concave down. So let me explain what those are. Concave up would be this type of graph. Concave down would be this. So sometimes they like to say holding water in a concave up, okay, type of graph. So this is concave up, this is concave down. Okay, one thing that's important to note is concavity test only tells us about the behavior of the graph. It doesn't give us any particulars about the critical values for the second derivative. If we take a look at the graph here in figure 4.41, you will notice that the concavity of this curve changes several times throughout this domain. One way that we can determine this is that if I were to draw tangent lines along any portion of the graph, I would notice that at some point the tangent line moves from the top of the graph to the bottom of the graph. So if I am drawing the tangent line to the curve of a section that's concave up, my tangent lines are on the bottom of the graph, and also in this interval as well. But when I am drawing tangent lines on a section of the graph that's concave down, you'll notice that my tangent lines are on the top here and here as well. Okay. So important to point out, the point on the graph where the concavity changes is called an inflection point. So for this graph in particular, B is an inflection point, C is an inflection point, D is an inflection point, E is not an inflection point, but P is an inflection point. The reason E is not considered an inflection point because it was concave up to the left of E, and it is also concave up to the right of E. Let's move it on. Let's get into the procedure for finding our inflection points. All right, so here are the highlights. If you want candidates for inflection points, you have to find where your second derivative is equal to 0 or where your second derivative does not exist. All right, so it's kind of the critical values, if you will, for the second derivative. And once you have those candidates, you have to check to make sure that the concavity changes on both sides. If a change in the sign occurs, then it is a point of inflection. It's kind of like when we were using the first derivative test. And if my derivative went from positive to negative, then I knew I would have a maximum. Okay. So you had to have that change in order to say that it was a max. Well, if you don't have the change, then you can't say it's a point of inflection. All right. So if there's a change, it is a point of inflection. All right. So let's move into the second derivative test. See, this is the title of this entire lesson, and it took us 10 minutes to get to this box. It says, if your function is continuous and differentiable, that's like the primary criteria. But once we know that our function is worthy, then we can apply this test to find our local maximums and minimums. If your derivative is equal to 0, and if your second derivative is greater than 0, then you can say that at this particular point C, you have a local minimum. What we're talking about is a derivative of 0, and concave up. Well, of course, this is going to be a minimum. And likewise, it says if we have a derivative of 0 and the graph is concave down, well, then this is a maximum. So that's my second derivative test. Let's move it on. Here's our example. It says, let f of x be defined as shown. Find the intervals where we have increase or decrease and find the local extreme values. Then it says find the intervals where we have concave up or concave down and find the inflection points. Part C, we will not do for this problem. We will analyze our first and second derivatives. So let's get started. First thing we need to do is to find the first derivative. So take a look at this function. You can find the derivative in whichever manner you so choose. You can expand and combine all of this together, or you can do that product rule and chain rule combined together. I'm going to do the product and chain rules.
Just eat food, try not to be crude or rude. Kill the attitude, chill the serious mood, and do what you like. And do what you like. Everybody do what you like.
Now that I have my derivative, I am going to locate my critical values.
Yeah, do what you like. Just do what you like.
I'm going to do our sign chart here. We are concerned with what's happening in between these intervals. So I'm going to choose values, just anything in those intervals. So this is going to be negative, negative, that makes this positive, positive, negative, that makes this negative. Okay, so my derivative, positive, negative, positive, that means that my function is increasing, decreasing, and increasing in these intervals. This is a local max, and positive 1 is a local min. We're going to find out what those values are. Plug those values in to figure out what our max and min values actually are.
It's the underground. You know that we're down with what you like. With what you like. And though we're usually on a serious tip, check it out. Tonight we're gonna flip and trip and let it all hang out tonight.
So in part B, we are finding concavity and inflection points. Therefore, we have to analyze our second derivative. So starting at the first derivative, let's find the second. And if we set this equal to 0, we end up with an x value that's equal to 0. So this is a possible inflection point. We do not know for sure, but we have to check. Okay, so just like before, we're going to make ourselves this little sign chart. And here I have an x value of 0. Well, let's consider what happens on both sides of this value. So if I were to put in something negative into this second derivative, then I end up with a negative value. If I put in something positive, I get a positive. There's no need for like an elaborate chart when you have something simple such as what we have in this case. So my second derivative, okay, so let's talk about how that affects my function. So if my second derivative is negative, then that means that my graph is concave down. And when it's positive, we have up. Because the concavity did change from left to right, we can thus say that this is in fact an inflection point because the concavity did change. Inflection point is located at x equals 0, but let's figure out what the value of the function is at that location. Okay, so let's summarize.
It's the underground. You know that we're down with what you like. With what you like.